Hello and welcome to this video lesson. In this video lesson we will be looking at vectors in 3D. We're going to start by looking at a point. Here we have point A, which has x coordinate of 5, y coordinate of 2, and z coordinate of 8. Now, if we start a vector at the origin, point 0, 0, 0, and move it in the x direction by 5, in the y direction by 2, and in the z direction by 8, we get vector OA. Vector OA starts at the origin and terminates at point A. Now, just a reminder that base unit vectors are vectors that have a magnitude of 1. Base unit vector I goes in the x direction, j goes in the y direction, and we're introducing a new one, k, today, which moves in the z direction by magnitude of 1. Using the base unit vectors, we can write our vector OA as 5i plus 2j plus 8k, and this is the unit vector form. Now, if we have a vector v, which has x component of v1, y component of v2, and z component of v3, then we can find this magnitude by taking a square root of v1 squared plus v2 squared plus v3 squared. So, for instance, for vector OA, the one in the diagram, its magnitude can be found by taking a square root of 5 squared plus 2 squared plus 8 squared. Now, if our vector doesn't start from the origin, so if we have point A, which has coordinates of x1, y1, and z1, and point B, which has coordinates of x2, y2, and z2, and if these are 2 points, then vector AB, or position vector of B relative to A, can be written as vector AB, which is OB minus OA. OB being vector B, which starts at the origin and terminates at point B, and vector OA being a vector which starts at the origin and terminates at point A. We can find the resulting components of vector AB by subtracting the coordinates, the x coordinates of B from A, y coordinate of B from A, and z coordinate of B from A. Once we have the components in x, y, and z direction, we can actually find the magnitude of vector AB by simply taking the square root of its x component, y component, and z component. And you can see that the magnitude of vector AB is the square root of x2 minus x1 squared, which is the x component, plus y2 minus y1 squared, which is the y component, plus z2 minus z1 squared, which is the z component of vector AB. Now, very similar to two-dimensional vectors, in three-dimensionals, two vectors are equal if they have the same magnitude and the same direction. So, given two vectors, vectors A and vector B, vector A having x component of A1, y component of A2, and z component of A3, and B having x component of B1, y component of B2, and z component of B3, vector A will equal to vector B if and only if A1 is equal to B1, A2 is equal to B2, and A3 is equal to B3, meaning that the x component, the y component, and the z component of the two vectors are exactly the same. Now, if vector A and vector B do not coincide, meaning that they're not on top of each other, that means that they are on the same plane. So if you take a piece of paper, both vectors can be drawn on that piece of paper, and that they are opposite sides of a parallelogram. So you can see in the image that if you draw the two vectors and if they're equal and they don't coincide, they can form a parallelogram. Alright, let's look at two examples. In the first one, we're given 2 points, point A and B, and its x, y, and z components. And we want to find vectors OA, vectors OB, and vector AB. The second question gives us 4 points. It gives all the coordinates of point A, B, and C, but leaves the coordinates of point D as unknown. And it says that if vector AB is equal to vector DC, find the missing values. We're going to start off the question with writing the x, y, and z components of the origin, which are all 0. So if we want to find the vector OA, we have to subtract the x, y, and z components of O from A. So 2 minus 0 gives us 2, 1 minus 0 gives us 1, and 5 minus 0 gives us 5 as the x and y and the z components of vector OA. We're going to use the same logic because any number minus 0 is itself. Vector OB becomes -1, 3, -1. Now, for finding vector AB, we are going to subtract the x, y, and z components of vector A from B. So we have -1 minus 2, 3 minus 1, and -1 minus 5 for the x, y, and z components of A and B, resulting in -3, 2, and -6. We could also write the answer in unit vector form as -3 times vector I plus 2 times vector j minus 6 times vector k. Now, to start the second question, we have all the values for point A and B, so we can simply find vector AB by subtracting components of A from B. So we go 2 minus -1 for x components, 5 minus 3 for the y component, and -1 minus 4 for the z component, giving us 3, 2, and -5. To find vector DC, we are going to subtract components of vector D from C. So we have -1 minus R, 2 minus S, and -2 minus T. As we said previously, for vector AB and vector DC to be equal, all of their components have to be exactly the same. Therefore, -1 minus R should equal to 3, 2 minus S should equal to 2, and -2 minus T should equal to -5. Now we can solve each one of these. For the first one, we can add R to both sides and subtract 3 from both sides, and we get R equals to -4. For the second one, we add S to both sides and subtract 2 from both sides, and we get S is equal to 0. And finally, for the last one, we add T to both sides and add 5 to both sides, and we get T is equal to 3. Okay, now let's look at some properties of vectors. So the properties that apply in 2D also apply in 3D. So given vector A with x component A1, y component A2, and z component A3, and vector B with x component B1, y component B2, and z component B3. If we multiply any of these two vectors, let's say vector A, by a scalar value, then the components of that vectors will all multiply by that scalar value k. So for example, if vector A was 1, 2, 3, multiplying it by scalar value of 2 will give us 2, 4, and 6. If we add two vectors, A and B, all their components will be added up, and if we subtract two vectors, all their components are subtracted. Here are some other properties. So the first one we'll look at is the additive identity, meaning that if we add a vector to a zero vector, that is equivalent to a zero vector being added to a vector, which is just equal to that vector. For example, adding vector 1, 1, 1 plus 0 will simply equal to vector 1, 1, 1. The additive inverse property says that if we add a vector by its negative, that's same as adding a negative vector by the vector, which will result in a zero vector. So vector 1, 1, 1 plus vector negative 1, negative 1, negative 1 will give us a zero vector. The next property is the commutative property, and that says if we add vector b to vector a, that's same as adding vector a to vector b. So for example, vector 2, 2, 2 plus 1, 1, 1 will give us 3, 3, 3, and if we add 1, 1, 1 plus 2, 2, 2, we will still get 3, 3, 3. The associative property says that if we add three vectors, a plus b plus c, doesn't matter whether we put the brackets on a plus b or b plus c. The distributive property says that if we multiply a scalar value k by a plus b, or vector a plus vector b, it's equivalent to scalar value k multiplied by vector a plus the scalar value k multiplied by vector b. Now, if you have a case where we're multiplying a scalar by vector a, that means that k times vector a is parallel to vector a. Then if we take the magnitude of k times vector a, that is actually equivalent to the magnitude k multiplied by the magnitude of vector a. So we can kind of separate their lengths. Now, some other useful properties that you should remember. One is if we have a scalar value k multiplied by vector a is equal to vector b, then that means that vector a is equal to 1 over the scalar value multiplied by vector b. Now, in writing this, make sure that you don't write it as vector a is equal to vector b over k. It doesn't work the same way that we do work in algebra. So don't write it like this. Make sure that you always write it as vector a is equal to 1 over k, so have the scalar value separate multiplied by vector b. Finally, if we have vector a plus vector b is equal to vector c, then we can find vector a by simply subtracting vector b from both sides, which gives us vector a is equal to vector c minus vector b. Let's look at a few examples. The first example says that if vector ab is equal to I plus 3j minus 4k, and vector bc is equal to negative 3i plus 4j plus 4 times k, find vector ac. Now, when I say I, j, and k, I'm referring to vectors I, vector j, and vector k. So, vector AC is actually equal to vector AB plus vector BC. So you can see this by the diagram here. So here we're adding vector AB and BC, and the resultant vector will originate from point A and terminates at point C. So when we write it that way, then the rest of the question becomes very easy. You're just adding all the components. So you're adding vector I plus 3 times vector j minus 4 times vector k. And to that you're adding vector bc, which is consisted of components negative 3 times vector I, 4 times vector j, and 4 times vector k. You add the vectors I together, gives you negative 2 times vector I, 3 times vector j plus 4 times vector j gives us 7 times vector j, and negative 4 times vector k plus 4 times negative 4 times vector k will cancel out, and we're left with negative 2 times vector I plus 7 times vector j, or in component form, negative 2, 7, 0. Now, question 2 says, given points A, B, C, and D, determine if the quadrilateral ABCD is a parallelogram. Now, the first thing we do with this question is actually draw out the shape. So here we have a parallelogram with vertices A, B, C, and D. Now, looking at the shape, we can find out all the vectors A, B, B, C, C, D, and DA. Or if we think about it more carefully, if vector AB and vector DC are the same, or if they're equal, and if vector BC and vector AD are equal, that means that it is a parallelogram. So vector AB, we find it by subtracting components of point A from point B. So negative 1 minus 5 gives us negative 6, 2 minus 0 gives us 2, and 4 minus 3 gives us 1. For vector BC, we subtract components of point B from point C. So we get 4 minus negative 1, which gives us 5, negative 3 minus 2, which gives us negative 5, and 6 minus 4, which gives us 2. Now, we looked at AB. Now, if vector DC is the same, that means that vector AB and vector DC are equal. And for a parallelogram, of course, these two have to be equal. So x component 4 minus 10 gives us negative 6, negative 3 minus negative 5 gives us 2, and 6 minus 5 gives us 1. So vector AB does equal to vector DC. Let's check vector AD. Now, the reason we chose AD instead of DA is the direction, because we want to make sure that we're looking at the proper direction, and in this case, for the directions to work out, we should be looking at vector BC and comparing it to vector AD. And when we do the proper calculation, we do find that vector AD does equal to 5, negative 5, 2. And since vector AB is equal to vector DC, and since vector BC is equal to vector AD, we can conclude from this that the shape is a parallelogram. Now, for our last example, we are given an equation, and we're not given the scalar values A, B, and C, and that's what we're asked for. So we're asked that if scalar value A multiplied by vector 1, 1, 0 plus scalar value B multiplied by vector 2, 0, negative 1 plus scalar value c multiplied by vector 0, 1, 1. So all of those addition, if they equal to negative 1, 3, 3, then what is the scalar values a? What are the scalar values a, b, and c? Now, if these additions are equal, that means the x components should equal, the y components should equal, and the z components should actually equal. So 1 times a plus 2 times b plus 0 times c, which is 0, should equal to negative 1. 1 times a plus 0 times b plus 1 times c should equal to 3. And finally, for the z components, 0 times a plus negative 1 times b, or just negative b, plus 1 times c should equal to 3. Okay, now we can solve this in many different ways. The way I have done it is I've labeled my equations 1, 2, and 3. I've decided to subtract 2 from 3, and there's an advantage to doing this because the c's cancel out, the constants cancels out. So then I can substitute things that are a little bit easier as compared to if I had subtracted any other equations. If I had subtracted other equations, I would have gotten the correct answers anyways, but doing this helps a little bit. So a minus 0 gives me a, 0 minus negative b gives me positive b, c minus 0 is 0, and 3 minus 3 is 0. So that means that if I rearrange this, I get that a is equal to negative b. Now I'm going to sub a is equal to negative b into my first equation. So instead of a, I'm going to replace it by negative b. Negative b plus 2b is equal to negative 1. Negative b plus 2b is positive b, and that is equal to negative 1, meaning that b is equal to negative 1. Now, I have found one of my answers, so I'm going to sub that b is equal to negative 1 into the first equation. So now I get a plus 2 times negative 1 is equal to negative 1. That means a minus 2 is equal to negative 1, and if I add 2 to both sides, I get a is equal to 1. Finally, I'm going to sub a is equal to 1 into the second equation. I could sub b is equal to negative 1 to the third equation as well, and I get 1 plus c is equal to 3, meaning c is equal to 2. And I'll just write my final answer as a is equal to 1, b is equal to negative 1, and c is equal to 2.